In this video, I'm going to work through about 5 examples of using the law of universal gravitation. So, the first one, we're not given a whole lot of information, but it wants to know a number. The distance between two masses has doubled. By what factors does the gravitational force change? So what we have are two masses. Here they are, M1 and M2, and let's let this distance just be R, and then it doubles, so from there to, that looks roughly double to me. So now here is M2, so that means this distance is 2R. If we think about our original force, it's the gravitational constant, mass 1 and mass 2 all multiplied together, divided by our original r squared. And our new force is g m1 m2 divided by our new distance squared, which is 2r squared. Okay. Now I'm going to play around with this bottom form. Okay. 2 squared is 4. R squared comes along for the ride, and now I'm going to look, I'm going to even just change pen color so that you guys can see this easy. And I'm going to combine that much of it. And I'm going to look and say, hey, look, that's just what we started with. Okay, changing back to red. So if this is our original force and this is our new force, that means that F new is 1/4 our original force. So by what factor does the gravitational force change? It is 1/4 the original force. Okay. Example 2 is very similar to example 1. Here we have M1, we have M2, and they're separated by some distance r. And like the last one, we're going to change what the radius is, what the distance is. So in this case, instead of getting bigger, it gets smaller. So let's see, if that's half of where they were, and this is half again, so now they're like this far apart, because it's gone down by a factor of 4. So this is supposed to be 1/4 r. Ooh, that doesn't look much like a 4. Hopefully you can read that okay. Okay, our original force, just like in the previous example, is g m1 m2 divided by r squared. Our new force is going to be g m1 m2 divided by 1/4 r squared. Okay, and as before, I'm going to take and just get rid of those parentheses. Gm1, m2 divided by 1/4 squared is 1/16 r squared. And now I'm going to do the same thing and group, and notice that this much is that. This means that the new force is F old divided by 1/16. Now, maybe you remember, maybe you don't, maybe you just want to plug it into your calculator and check. But the denominator of the denominator, when you have an improper fraction, turns out to be the numerator. So that flips up to the top and it becomes 16 times our original force. So when the distance has decreased by a factor of 4, the force increases by a factor of 16. Again, this is a property of it being an inverse square law. When r goes up, F goes down by a factor of the change in r squared. And conversely, if r goes down, F will go up by a factor of the change in r squared. Okay, let's go look at our next example. How big is the gravitational force between the Earth and the Moon? Well, I mean, you guys all know my artistic skills here by now. Here's the Earth. You can tell because it's got an E. Here's the Moon. Oop. Well, it should have been the Moon, except it didn't like it. There we go. There's the Moon. It's got an M, kind of, right? They are separated by a... oh, it just disappeared. Let's try again. Honest. I want... Here, we'll do it this way. Moon. Right? They are separated by a well-known distance. The distance from the Earth to the Moon. If you look in the cover of your book or ask Dr. Google, you will see that the distance from the Earth to the Moon is 3.84 times 10 to the 8th meters. While I'm here, a couple other things I'm going to need is I need the mass of the Earth, which is also in your book, at 5.98 times 10 to the 24th kilograms. I'm also going to need the mass of the Moon, and that is 7.36 times 10 to the 22nd kilograms. We want to know the gravitational force, so we use the law of universal gravitation. Our two masses in this case are the Earth and the Moon, and the distance between them is the Earth-Moon distance. G has a value of 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the Earth, we just looked it up, is 5.98 times 10 to the 24th kilograms. The mass of the Moon is 7.36 times 10 to the 22nd kilograms. And we got to divide by that distance squared, 3.84 times 10 to the 8th meters squared. Now, if you put this all into your calculator, 6.67 times 10, me and my calculator are having problems. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 7.36 times 10 to the 22nd divided by 3.84 times 10 to the 8th squared. That gives you a force of 1.99 times 10 to the 20th newtons. For the next example, it says you're given the masses of the Earth and the Sun and the gravitational force. How far away is the Sun? So it wants to know the distance from the Sun to the Earth. So as always, I'm going to begin by drawing a picture. I'm going to draw my Sun bigger. Obviously, it should be much bigger than the Earth, but after all the trouble I had with the Moon, we're going to use big pictures. So, distance from the Earth to the Sun, our Sun. We know the mass of the Earth from the previous problem, but I'll just write it down again because it can't hurt. That's 5.98 times 10 to the 24th kilograms. The mass of the Sun is 1.99 times 10 to the 30th kilograms. And the force, oops, I clicked a button. The force is given right up here. So again, we use the law of universal gravitation. One of our masses is the Earth, the other one is the Sun. There's our distance squared. We want to know the distance, so I'm going to rearrange the formula for it. So that when I plug in numbers, all I got to do is punch them into my calculator. Okay, so big G is a constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the Earth is 5.98 times 10 to the 24th kilograms. Mass of the Sun is 1.99 times 10 to the 30th kilograms. And the force, you're told, is 3.53 times 10 to the 22nd newtons. So if I put that into my calculator, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 1.99 times 10 to the 30th, and divide by 3.53 times 10 to the 22nd, I get out 2.24 times 10 to the 22nd meters squared, because I'm still in squared up here. To find the actual distance, I have to take a square root. And that results in 1.49 times 10 to the 11th meters. Now you can either ask Dr. Google, or you can consult the cover of your book. I'm looking at the cover of your book, which tells me that the distance from the Earth to the Sun is 1.5 times 10 to the 11th meters. And for our last example, we're going to ask, what is the acceleration due to gravity on the moon? So here is the scenario. I have the moon, creatively labeled with an M, and I have an object like a ball very, very near the surface. Right. That ball has one force on it. It is the gravitational force. So we're going to pull in Newton's second law, F net equals ma, where this m is going to be the mass of the ball, because we're looking at the ball's free body diagram. If you want, alternatively to labeling this force due to gravity, you could call it the weight of the ball on the moon. So weight caused by the moon on the ball. Either way. But that is the force causing the net force. And it has to be given by universal gravitation. Now, the question is, what is this r? Well, we want to be near the surface of the moon, so certainly we have to include the radius of the moon. And looking at the cover of your book again, we see that the radius of the moon is 1.74 times 10 to the 6th meters. And we're near the surface. So this is 1.7 million meters. If we add even a couple hundred on, do you think it's going to make a huge difference? Try it, but really no. Okay. So the numbers we plug in, well, before we can plug in, notice we have a mass of the ball on this side and a mass of the ball on the other side, and so we can cancel it. So acceleration doesn't depend on mass. G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the moon is given in the cover of your book as 7.36 times 10 to the 22nd kilograms. And the radius of the moon, we looked up already, 1.74 times 10 to the 6th meters, that whole thing squared. So 6.67 times 10 to the minus 11 times 7.36 times 10 to the 22nd divided by 1.74 times 10 to the 6th squared. And that gives me out a value of 1.6 meters per second squared. Now, if I take the acceleration due to gravity on Earth of 9.8 meters per second squared and divide by 1.6 meters per second squared, that equals 6.125. So you may hear that the acceleration due to gravity on the moon is roughly 1/6 what it is on Earth. Here's the ratio that proves that, right? The acceleration due to gravity on the Earth is about 6 times the acceleration on the moon.